is finite.
Oh, A is finite. Oh, sorry.
Yeah. Okay. Absolutely. Any questions so far? I mean, this is quite, I don't know, but I think it's quite deep and has to be digested well.
What was the explicit definition of circulation again?
It's the, you can think of it as a global measure of rotationality. If you have some blob of fluid that is globally rotating, then there is a circulation. So the mathematical definition is the integral of our closed curve of u dot dx.
Sir, so can you say like at the trailing edge, like there's finite velocity just because the main reason is because of the conservation of circulation?
Well, it's a consequence. It's a consequence. Yes. Any questions so far?
But even if it is finite velocity, it is still not a stagnation point. I mean, at the stagnation point, the velocity is be zero, right?
Yes, you're right. We have both here. Yeah. So this is stronger than this thing. I'm saying equivalent in the sense they will lead to the exact same formula for gamma. You're right.
Oh, okay, I see.
Yes, Lynn?
So you said that like at the leading edge, the flow velocity is like actually infinity, like in physically it's.
I mean, physically there is no infinite quantity. Okay, so the flow velocity is very, very high because actually the flow turns around the leading edge,
Right.
and this turn is a very steep turn, so you have very high suction pressure, which is associated with very high turn velocity.
But it's like infinity according to our theory.
Yes, why? Because according to our theory, if I have a corner and if my flow turns around the corner, I should get infinite velocity. Okay. Yes, Anshul?
Does the Kutta condition only apply for sequential flow? Because if you have separation, then will it still...
Well, this is what Sir Kutta hypothesized. It's for attached, steady, small angle of attack, high Reynolds number. This is the main statement. The fact that we don't have an alternative, unfortunately, pushes or urges people to use the exact same thing with high angle of attack, separated flow, and you will see it in papers in the JFM very recent. I mean, there is no alternative. Yeah, people use it all the way. Any question?
Sure, one doubt, like so far the leading edge, that means, does it mean that physically it's possible to go to a really high velocity? Like not infinite.
I'm sorry, say it again. For the leading edge.
For the leading edge, like then does it mean that physically it's possible to go to a really high velocity?
It goes to very, very high velocity. I'm saying that it's not infinite. It's still finite. It's very, very high. So when you are in an ideal theory like this, you will get infinite. You see what I'm saying? It's very high. So the infinite value here, the infinite value of the pressure or velocity here is an idealization of a very high velocity or pressure in reality. If I have a very high velocity or pressure over there as well, we would have admitted the singularity and did not remove it. But because we did not have such a peak in reality, Kutta said that, well, we have to remove it. Okay? So some people, the mathematicians, they like to refer to the Kutta condition of the condition of least singularity. It's that whenever you have a singularity, remove it at the sharp edge. Sometimes it's called like this. Any questions? So we're done with this part. We got the flow around flat plate. We killed it, and we have our form. And I'll stress this even more. Look at this, because this is very important. 2 pi alpha. This is the ubiquitous left-to-left CL alpha curve that we use in our all undergraduate courses and graduate, and like I said, in airplane design and everything. They are all variations of 2 pi alpha. They are all variations of 2 pi alpha. So, how did we come at the 2 pi alpha kind of thing? It's Navier-Stokes equations, right? Then a brilliant assumption. So we came up with this, right? Okay, so the Navier-Stokes equation is one in the derivation, the development of Navier-Stokes equation. This is milestone. Then this assumption is a milestone, right? Then the observation from complex analysis, that these guys satisfy Cauchy-Riemann equations and the introduction of f equals phi plus I psi, this comes from complex analysis, right? Then another thing from complex analysis is conformal mapping. So before this allowed superposition. We have Laplace square f equals 0. We have superposition. So another milestone is that we added some elementary flows to get flow around a circular cylinder, right? Then we have another thing from complex analysis. We have the conformal mapping. Right? What we got here? We got the flow around. So this is conformal mapping. We're not there yet, actually. Conformal mapping, that's fine. Another milestone is that, okay, conformal mapping can map you to interesting shapes, but what is the particular shape, what is the particular map that maps me to a flat plate? So this is Joukowsky transformation. Okay? Then I have what? Now immediately I have the flow around the flat plate. Okay? But gamma, right? So then the final, the punchline that finished it is the Kutta condition. Gives you the final result. CL is 2 pi sine alpha or 2 pi alpha. This is a paradigm for the accumulation of signs. Look at this result. Look at how many, any red thing here is a milestone. And any red thing here was a necessary component to arrive here. If you removed any of these red things, you will not arrive here, which has enabled the aviation history. Well, the Wright brothers, they flew without 2 pi sine alpha. But to proceed after the Wright brothers and to develop the early generation, the DC-3 and this generation, this was essential. And if you read the papers of the early pioneers, they all commend the lifting line theory and thin fold theory. They did great things with these tools. The Navier-Stokes equations, a brilliant assumption, tools from complex analysis, the exploitation of a mathematical principle, we arrive here. Then another tool from complex analysis, it's not aerodynamics. Then a development. Then finally, even after all this, it's still waiting here. And the punchline from physics, right? That finished it. It's, to me, this is indeed, it's a paradigm for how science evolves. This is how science evolves. It cannot be just, here is a single thing that you'll finish everything. No, it's a stone, stone, stone. You have your building at the end, this is the final result. Okay? Any questions so far? Very good. So, okay. So how to proceed further? We got the flow around the flat plate, and we want to do flow around more complicated shapes. Yeah, there are two main approaches. First, the method of conformal mapping, and you can imagine what is this. So in this method, if you have some shape, the problem problem just reduces to finding the mapping that gets you from here to there. What is F? So it's not a fluid mechanics problem, it's pure geometry now. What is the function, what's the conformal function in the complex domain that gets me from a circular cylinder to my shape? I'm given this shape. I want to solve the flow around this shape. And this is still an active research area actually, by the way. Okay? So what is F that maps me from here to there?